Something happened yesterday that scientists don't take lightly. In a single day, within just a few hours of each other, a cluster of powerful earthquakes hammered the coast of Northern California and Southern Oregon. Not one, not two, a sequence. Multiple strong strikes, back to back, in one of the most geologically volatile and watched regions on the entire planet, and now people are asking the question out loud, the one that geologists have been quietly preparing for decades. Is this it? Is the big one finally waking up? Let me be straight with you from the start. I'm not here to scare you. I'm not here to tell you the ground is about to swallow the West Coast. But I am here to tell you exactly what happened, why scientists are paying very close attention, and what you need to actually understand about this region if you live anywhere near it, because the geology here is unlike almost anywhere else on Earth, and most people have no idea what's really going on beneath their feet. So let's go. The first major earthquake struck about 100 miles, roughly 160 kilometers. West-northwest of Crescent City, California. The magnitude came in at 5.7, though some agencies clocked it at 5.8. That's not a minor tremor. That's a significant earthquake. The depth was approximately 10 kilometers, which puts it in shallow territory. The kind of depth that sends energy very efficiently through the crust and gets felt across a wide area. And here's the first thing that jumped out to seismologists immediately. This earthquake did not occur on the boundary between tectonic plates. It occurred inside a plate, specifically inside the Gorda Plate. That distinction matters enormously, and we're going to come back to it. Then, just 2 hours later, a second significant earthquake hit. Magnitude 5.1, near Petrolia, California, a town that sits right on the edge of one of the most tectonically complex intersections on the planet. And then the aftershocks started rolling in. At 4.5, multiple events in the 4+ range. Smaller quakes filling in the sequence. By the end of the day, the southern part of this region had experienced a level of seismic activity that made monitoring agencies sit up and start making statements. The Redwood Coast Tsunami Work Group, a scientific body that exists specifically to track the hazard potential of this coastline, issued a finding that stopped a lot of people in their tracks. Their assessment was that the 5.7 and the 5.1 were probably not directly related to each other. Two major earthquakes within 2 hours in the same general region, and scientists are saying they likely came from two completely separate tectonic systems firing off on the same day. Think about what that means for a moment. This wasn't one fault having a bad day. This was multiple systems under elevated stress, simultaneously expressing that stress in the same geographic window. That is not something you wave off. To understand why this matters so much, why and why it matters for the broader Cascadia question that everyone keeps asking about, you have to understand the bizarre, brutal, almost uniquely chaotic geology of this corner of the Earth. Because this isn't just a place with a fault line running through it. This is a place where multiple tectonic plates are colliding, grinding, diving under each other, and in one case, literally being crushed from both sides at the same time. But there is no other place quite like this on Earth in terms of layered geological complexity, and that complexity is exactly why scientists watch it as closely as they do. Start with the big picture. The west coast of North America sits on the edge of the North American Plate, the continent you're standing on if you're in the United States. Out in the Pacific Ocean, you have the Pacific Plate, which is one of the largest tectonic plates on the planet. Between them, off the coast of the Pacific Northwest, you have a smaller plate called the Juan de Fuca Plate, which is actively subducting, meaning it's diving under the North American Plate. That subduction zone is the Cascadia Subduction Zone. It runs roughly 700 miles from Northern California all the way up to British Columbia and Canada, and it is capable of producing what scientists call a megathrust earthquake, a full margin rupture that could reach magnitude 9.0 or higher, triggering a tsunami that would devastate the entire Pacific Northwest coast within minutes of the earthquake striking. Scientists know this because it has happened before. On January 26, 1700, the Cascadia Fault ruptured in a massive megathrust event. We know the exact date because of Japanese records documenting the orphan tsunami, a tsunami that arrived on the Japanese coast with no corresponding earthquake felt locally. Indigenous oral traditions along the Pacific Northwest also preserved accounts of a great shaking and a wall of water. Tree ring data, buried soil layers, offshore turbidite deposits, the geological record is clear. Cascadia breaks. Cascadia produces catastrophic tsunamis. And based on the average recurrence interval, Cascadia is overdue. Not in a casual, don't worry about it overdue. This fault has historically ruptured every 200 to 500 years, and it has now been 325 years, kind of overdue. That is the shadow hanging over every single earthquake that happens in this region. Every tremor, every swarm, every cluster of activity gets measured against that backdrop. So when you get a day like yesterday, multiple strong quakes, separate tectonic systems, elevated stress signals across the entire southern Gorda region, you understand why the notifications start blowing up and why people who live along the coast start asking questions. Now back to the Gorda Plate, because this is where the story gets truly fascinating. The Gorda Plate is technically a fragment of the Juan de Fuca Plate. This is the southern section of it. And it has a problem that most tectonic plates don't have. Most tectonic plates are relatively rigid. They move as a coherent unit, and their internal structure stays largely intact. The Gorda Plate is not like that. The Gorda Plate is being simultaneously squeezed by the Pacific Plate pushing in from the south and the process of subducting under North America from the east. The result is that the Gorda Plate is internally deforming. It's being crumpled. It's being torn apart from the inside. Scientists describe this as significant internal deformation, and what it means in practical terms is that the Gorda Plate has a dense network of internal faults, weak zones running through it in multiple directions, and those faults can produce earthquakes entirely within the plate itself, not just along its edges. This is why the 5.7 earthquake being located inside the Gorda Plate rather than on its boundary is scientifically significant. You don't expect that from a normal plate. From the Gorda Plate, it's actually consistent with its history. Look at the record: 1,980, magnitude 7.2, a Gorda Basin event, an intraplate earthquake, meaning inside the plate itself. 2005, another magnitude 7.2, a major intraplate strike slip event. Multiple magnitude 5 and 6 swarms over the decades, most of them west of Crescent City. Exactly where yesterday's 5.7 hit. The Gorda Plate has been doing this for a long time. It is, as scientists put it, one of the most deformed oceanic plates on Earth. So in isolation, an earthquake inside the Gorda Plate is not a direct Cascadia warning sign. It fits a well-established pattern of this plate behaving strangely because its fundamental structure is strange. But here's what makes yesterday different from a routine Gorda Plate earthquake. It's not just the 5.7. It's the 5.7 and the 5.1 on the Mendocino Fault and the aftershock sequence and the timing, all of it happening within hours. Let's talk about the Mendocino Fault because it deserves its own moment in this story. The Mendocino Fault is a transform fault. A strike slip fault, meaning the two sides are sliding horizontally past each other rather than one diving under the other. It's the southern boundary of the Gorda Plate, and it's already well established as one of the most seismically active fault systems in California. In 2024, there was a magnitude 7.0 earthquake sequence in this region. That's a very recent and very significant rupture. Transform fault sequences have long aftershock tails, meaning earthquakes continue to occur in the same area for months and even years after a major event. The 5.1 near Petrolia may very well be part of that tail. The Redwood Coast Tsunami Work Group suggested exactly this possibility, that the 5.1 is possibly related to the 2024 magnitude 7.0 sequence. So, what you may have had yesterday is a Gorda Plate intraplate earthquake on one side and a Mendocino Transform Fault aftershock, or stress-triggered event on the other side, both happening on the same day. Two different tectonic mechanisms, two different fault systems, both expressing activity within a short window. The interpretation that matters here is this: the entire southern Gorda region is currently under elevated stress. That isn't panic. That's what the data says. Now let's address the Cascadia question directly, because it's the one everyone wants answered and it deserves a straight, scientifically grounded response rather than either dismissal or catastrophizing. Does yesterday's activity increase Cascadia concern? The honest answer is a little, but not dramatically, and the reasons why are important to understand. The geographic argument for calm is real. The eastern edge of the Gorda Plate is the southernmost portion of the Cascadia Subduction Zone. But what was active yesterday is mostly the Gorda Plate's internal deformation and the Mendocino Transform system, not the megathrust interface itself. The megathrust interface is the part of Cascadia that actually ruptures in a magnitude 9 event. There were no clear signals yesterday of unusual activity specifically on that interface. There was no accelerating pattern of shallow offshore seismicity creeping northward along the full subduction zone. There was no GPS deformation signal, no tremor burst, none of the more direct indicators that the locked megathrust zone is about to let go. However, and this cannot be glossed over, tectonic stress is not perfectly isolated. Fault systems interact. When one system releases stress or shifts stress, it can affect the stress state on neighboring faults. That's basic physics applied to geology. A large rupture on the Mendocino Fault doesn't happen in a vacuum. Activity in the southern Gorda Plate changes the stress geometry in the region. Whether those changes are enough to push the Cascadia megathrust significantly closer to failure is not something we can calculate with precision right now. What we can say is that the southern end of Cascadia, which is already the most seismically active section of the subduction zone, is in a period of heightened regional stress. That is a factual statement. What it ultimately means for the timeline of a Cascadia megathrust event is genuinely unknown. The scenario framework that scientists work within for situations like this is roughly three-tiered. The most likely outcome, and this is the scenario that history strongly supports, is that the aftershock activity fades over the coming days and weeks, no major earthquake follows, and the region settles back into its background level of seismicity. This is what happens the vast majority of the time. The Gorda Plate has had dozens of swarms over the decades. Most of them end quietly. The second scenario is continued elevated activity, more magnitude 5 seconds, possibly a magnitude 6, representing ongoing regional stress release but still confined to the Gorda Plate and Mendocino system without direct Cascadia megathrust involvement. That's less likely than scenario 1, but not unusual for this region in the months following a significant sequence. The third scenario, low probability, scientifically important, and the one that would change everything, is if the seismicity migrates. If the locus of activity starts moving northward. If you start seeing clusters of earthquakes shifting toward the Cascadia interface. If offshore seismicity starts spreading along the subduction zone rather than staying concentrated in the southern Gorda region. That is the signal that would trigger a genuine escalated scientific response. That is not what we're seeing right now, but it is what you watch for. There's a broader context to all of this that doesn't get talked about enough, and it's this. The American public's understanding of Cascadia is dangerously underprepared for what the science actually says. FEMA's own projections for a full Cascadia megathrust rupture are sobering. The scenario involves ground shaking that lasts for 4 to 6 minutes across the entire Pacific Northwest, not seconds, minutes. It involves a tsunami that would reach some parts of the Oregon and Washington coast within 15 to 30 minutes of the earthquake. It involves projected casualties in the tens of thousands, with some estimates going higher depending on the time of day and the response. Critical infrastructure, bridges, highways, hospitals, ports, would be severely damaged or destroyed. The recovery timeline for a full Cascadia rupture is measured in years, not weeks. Some communities along the coast are so isolated that they would be on their own for days before outside help could reach them. Oregon and Washington have made significant investments in tsunami preparedness. Vertical evacuation structures, public education, improved warning systems, but the gap between what the science says and what people are actually prepared for remains wide. A study from Oregon State University described a full Cascadia rupture as the worst natural disaster in North American recorded history. That's not hyperbole. That's what the models project. And the key word there is recorded because because the geological record shows that Cascadia has produced events of this magnitude before, repeatedly, over thousands of years. None of this means yesterday's earthquakes were a final warning, but they are a reminder. This fault is real. The hazard is real. The timeline is uncertain. It could be tomorrow or it could be 100 years from now. But the physics of this system have not changed. The plate is still subducting. The locked zone is still locked. The stress is still accumulating. It has been accumulating for 325 years. So, what should you take away from yesterday? First, that this is a geologically hyperactive region that produces significant earthquakes regularly, and that multiple fault systems activating on the same day is unusual enough to pay attention to, but not unprecedented. Second, that the Gorda Plate's internal deformation and the Mendocino Transform activity are the primary drivers of what happened yesterday, not the Cascadia megathrust directly. Third, that there are no current indicators of imminent megathrust rupture, but that the region is experiencing elevated stress, and scientists will be watching the pattern of activity carefully over the coming days and weeks. Fourth, and maybe most importantly, that regardless of whether yesterday was a foreshock sequence, a coincidental cluster, or a stress interaction, the Cascadia hazard exists independently of any single event. You don't need yesterday's earthquakes to justify preparing for Cascadia. The geology itself justifies it. If you live in the Pacific Northwest, Oregon, Washington, Northern California, and you don't have an earthquake and tsunami preparedness plan, that is the actionable thing that should come out of watching this video. Know your evacuation routes. Know if you're in a tsunami inundation zone, most coastal municipalities have these maps publicly available online. Have a go bag with supplies for at least 72 hours. Know what to do when the shaking starts? Drop, cover, hold on. And know this, if you're on the coast and you feel a major earthquake that lasts more than 20 seconds, you don't wait for a warning siren. You move immediately to high ground. The earthquake is the warning. Now let me circle back to something scientifically remarkable that this entire story connects to, and it's something that changes how we think about fault hazard assessment globally, including for faults like the San Andreas. Researchers have been studying a fault in the Pacific Ocean that does something extraordinary. It ruptures like clockwork. Same location, same magnitude. Every 6 years, not every few years approximately, every 6 years, with a precision that made seismologists think they were reading the data wrong the first time, and then it stops. The rupture doesn't grow. It doesn't cascade into a larger event. It doesn't hit a different section of the fault. It produces its earthquake, and then it goes quiet for another 6 years. For a long time, scientists couldn't explain this. Why would a fault rupture with such mechanical regularity? Why would it always stop at the same magnitude? What is controlling the size of the rupture so consistently? And the answer they eventually found has major implications for fault hazard everywhere. What they discovered is that the fault is constrained by what they call geometric and rheological barriers. Basically, the structure and material properties of the rock along that fault have natural stopping points. The rupture propagates until it hits a section of rock that is either too strong, too geometrically irregular, or too different in mechanical properties to allow the rupture to continue. And because those barriers are stable and consistent, the rupture always stops in the same place. The energy released is always the same. The pattern is locked in by the physical architecture of the fault itself. This is transformative for hazard science. Because one of the great uncertainties in seismic risk assessment is always, how big can this fault actually go? When you look at a fault like the San Andreas, you know its length, you can estimate its locked depth, you can calculate potential magnitudes, but predicting where a rupture will stop, how much of the fault it will involve, has always been deeply uncertain. If the principle discovered in this clockwork fault applies more broadly, if we can identify these natural rupture barriers in other fault systems, it could allow scientists to constrain the maximum magnitude of dangerous faults with far greater precision than currently possible. It could tell you not just that a fault can produce a big earthquake, but how big, where it will stop, what the realistic upper bound actually is for the San Andreas, for Cascadia, for subduction zones across the Pacific Rim. That kind of knowledge is game-changing. It doesn't eliminate the hazard. It doesn't mean a fault won't rupture, but it means you can build better models, give better estimates, design infrastructure to the right standards, and ultimately save lives at a scale that matters. Science often moves in increments that seem abstract until you realize what they add up to. This is one of those findings that adds up to something significant. Yesterday's earthquakes off the coast of Northern California and Oregon were real. They were significant. They were worth paying attention to. They activated two separate tectonic systems in a region that is already among the most hazardous on the continent. They came in a broader context of a seismically active year for the Pacific coast. And they happened along the southern edge of a subduction zone that the scientific community has been telling us for decades is capable of an event that would reshape the Pacific Northwest. But they did not, based on current evidence, represent a direct precursor signal to imminent Cascadia rupture. What they represent is a reminder. A loud, geologically meaningful reminder that the Earth underneath the Pacific Northwest is not quiet. It is not passive. It is a dynamic, actively stressed system that is building toward a major event. Whether that's in our lifetime or not is genuinely unknown. What is known is that the system is real, the hazard is real, and the time to prepare is not after the shaking starts. Keep watching this region. The next few days will be telling. If the activity fades, that's the most likely and most welcome outcome. If it persists, escalates, or starts migrating, if the seismicity pattern begins to shift in ways that suggest the stress is moving toward the main Cascadia interface, that is when the conversation changes. Stay informed. Stay science-based. And for those of you living along this coastline, know your ground. Know your route. Know what to do. Because the one thing that 325 years of geological silence guarantees is that the silence will eventually end.